So our next presenter is Loay Yari. Loay is a skilled embedded systems developer who's inspired by retro video game consoles. Who isn't? And driven by a keen interest in AI, machine learning, and data analysis. And the topic of Loay's talk is harnessing the power of TinyML and RT-Thread, efficient machine learning for real-time embedded systems. So take it away, Loay.
Hello, everyone.
Hey there, we can hear you.
Yeah.
Yes, we can see your screen. Awesome.
Oh, cool. Okay, I will start now. Welcome, everyone. Today we are going to talk about TinyML, an exciting field of machine learning aimed at bringing intelligent capabilities to extremely low power and small form factor devices. We will explore its benefits, its application, and the challenges of running machine learning algorithm on resource-constrained devices. By the end of this presentation, I hope that you will have a deeper understanding of TinyML and its potential impact. Before we delve into the content, allow me to introduce myself. My name is Loay, an embedded system developer with passion for retro video game consoles and like the 8-bit era. My journey in this field began during my studies. I started with the AVR microcontroller, the Z80 microprocessors, and since 2012, I have been extensively working with RT-Thread, starting with the version 0.1.0 on an STM32 Cortex M3, the F03VE microcontroller. Over the years, I have crafted customized drivers and BSP packages to support various hardware for my project. My interests also extend to creating tools for automating the development and testing process and emulating different architecture for educational and hobby purposes. I have worked with many open source and closed source solutions, and I keep myself updated with the latest trend in AI, machine learning, and data analysis. I'm excited to share with you my knowledge and experiences in leveraging TinyML with RT-Thread today. So, before we proceed, let's familiarize ourselves with some key terms and abbreviation we will be using throughout this presentation. TinyML stands for Tiny Machine Learning. RT-Thread is a powerful open source real-time operating system. In short, RTOS. Also, BSP stands for Board Support Package. Like as example, if we have a board like Arduino or any kit, let's say Raspberry Pi, we have some kind of preference that we need to determine which the pin name, port name, what any accessories or sensor on this board. So we create something called BSP for that. MCU and SoC, as everyone knows, is MCU stand for microcontroller unit and SoC is system on chip. AI is short for artificial intelligence. And the new abbreviation we'll get to know today is some tools and library, which CMSIS-NN stand for Cortex Microcontroller Software Interface Standard Neural Network from ARM. And ONNX is Open Neural Network Exchange. Lastly, ELL is the Embedded Learning Library. So first, let's get a brief info about the famous RTOS we are working on as all the team and community is the RT thread. RT thread is an open source real-time operating system designed for embedded systems, founded in 2006. It has a microkernel architecture and offers a rich set of component and feature tailored for embedded systems. At the beginning, when I first started my journey in embedded system, what attracted me about the RT thread is the nice community and the feature when you get it, like the first one, I feel it's more useful for beginner when using the RTOS was the shell, the component that have in RT thread. So when you write any function and you want to test it in live, like any command line when you use it on Linux, it was available on the microcontroller, which was speeding up the development process when writing any application on the system. So let's go to the feature basically of the RT thread. RT thread come with a range of features, including modular design. As it's modular, meaning that developer can enable or disable the components as per their need. And before that, we used the scones environment tool, like from the command line. Basically, it's a Python script, similar like how we do the CMake or the Makefile. But now it's get more extended that we have the RT Thread Studio. So we have a package support. We can open it and install any new component shared by the community who participate in growing the RT thread. Also, other feature is the POSIX standard compliance. This feature enhances portability and makes it easier for developers familiar with Linux to use RT thread. The device driver framework also it's offers by the RT thread, allowing developer to create and manage device driver efficiently. File system support, RT thread support range of file system, enabling it to handle data storage and retrieval tasks effectively. Like when you, the famous one is like FFS. There is also the device file system, which you can use it with any small footprint memories, like you can get some chunk of the flash memory or external NAND or NOR flash and manage the file using a small file system. Also have the networking support. So it's include networking protocols, which also based on other open source projects. Making it suitable for IoT application. So any SoC or any module based on Ethernet or Wi-Fi, it can be connected to the internet. So let's check also about the RT thread component, which can be broken down into three levels. The kernel layers, this includes the scheduler, clock management, memory management, device management, and other core components necessary for system operation. The second layer is the component and service layer. This comprises a rich set of middleware components, including shell command line interface, the one I mentioned it before, the file system, network framework, device driver, etc. The main, the high level, or let's say the main one, when the developer will get advantage and focus on the software when using the RT thread is the application layer. So this is where user application and task are executed. Let's get to the benefit if when using the RT-Thread for embedded system in general. The capability, it will provide deterministic response times, which are crucial for many embedded systems. And modularity. The RT-Thread modular design allows the developer to use only the component they need, conserving system resources. Like, let's say we have a big project. We started with microcontroller, have like 250K of flash and let's say 64K of RAM. Then we want to make the cost reduce version of the project with less resources microcontroller. Let's get down to the 20K RAM and 64K of flash memory. So in that case, we can get rid of some feature. Like let's say we need only the ADC part, the RTC timer, the I2C, and we remove any other part which is not necessary for the reduced version. Like the USB port is not necessary. That this will be easy when using the RT-Thread Studio. About the community support, as an open source system, RT-Thread has a vibrant community that contribute to its development and provides support to users. So we have the website. You can ask any question and the developer will answer. Also, if you are in, let's say what I see here, while I living here in Shenzhen since 2012, before the RT-Thread get popular, there was like the private QQ for developers, and from there I get introduced to Bernard and the other team, where they helped me a lot during my development. Also, the rich middleware component. This one, the set of middleware component provided by the RT-Thread helps accelerate the development of embedded applications. And the reason of this presentation actually to encourage developer to try to manage to add as much as possible TinyML framework support to the RT-Thread. As what I see, there are many examples on Mbed, on Arduino, and this can be easily ported. So what we can get the benefit from using both RT-Thread and TinyML is improved task scheduling in RT-Thread or similar RTOS. There is a built-in scheduler to manage different tasks. This enables more efficient task scheduling than would typically be possible on bare metal systems, leading to improved performance. It also provides real-time scheduling, which ensures tasks with high priority are given access to the CPU as soon as they are ready to execute. Also, we will have enhanced resource management. RT-Thread allows for more sophisticated resource management, enabling optimal use of the available CPU, memory, and other resources. It can manage system resource and hardware, allowing tasks to share these resources effectively and avoid potential conflicts. This is especially beneficial in a TinyML scenario, where resources are often limited. Also, for the modularity, as we discussed, application can be broken down into separate tasks or threads, leading to a more modular design. This modularity simplified coding, debugging, and testing of complex applications. It also allows developers to reuse code across different projects, increasing development efficiency. Also, we will get improved power management. Power management is crucial for device running on batteries or harvesting energy. RT-Thread, like many other RTOS, offer power management feature. This allows the system to enter low power modes during periods of inactivity, saving energy. Such a feature is crucial in a TinyML context, where efficient energy use is a high priority. We have also better determinism. As a real-time operating system, RT-Thread can provide guarantees about the timing of task execution, which is known as determinism. This is critical for many TinyML applications, where timely response to sensor data is often necessary. Better determinism ensures predictable and reliable system behavior. So regarding for the hardware platform compatibility, in general with RT-Thread and TinyML, a quick research. Usually for using TinyML, the device some hardware platforms are capable of supporting RT-Thread and TinyML both. These platforms generally need to have sufficient computational power and memory to handle the demand of real-time tasks and execution of TinyML model. They range from powerful microprocessor to lower-end microcontrollers and various system-on-chips. As example of compatible hardware platforms, which basically RT-Thread is already supporting it. We can see the STM32 family, the H7, Cortex M4 also, and Cortex M3. From Cortex M, we can use one of the library to support it. But in generally, if we want to use a highly trained model, which need more constraint of memory, we need a higher memory and higher speed to get better implementation. So like NXP IMX series, the STM32H7 and the Raspberry Pi Pico can handle this implementation. Now going to the tools or name of the framework, which the developer can have look at it and start to see how they can implement it on the RT-Thread, as it's already implemented on other framework, open source framework, or as a bare metal or inside RTOS. The first one is the TensorFlow Lite for microcontroller. This one is an open source deep learning framework. It's provided by Google. It's a version of TensorFlow Lite designed to run machine learning models on microcontrollers and other resource-constrained devices. TensorFlow Lite for microcontroller is pre-configured with several sample applications and supports a variety of popular microcontrollers. What we can mention about that, like people who already have experience trying TensorFlow framework with Python, they can easily migrate or port it to the TensorFlow Lite framework. The other one is CMSIS neural network. Is from ARMS. This one can work with the ARM Cortex microcontroller. It stands for ARMS Cortex Microcontroller Software Interface Standard Neural Network Libraries. It's a collection of efficient neural network kernels developed to maximize the performance and minimize the memory footprint on ARM Cortex-M processors. It's an essential tool for developers looking to run machine learning models on resource-constrained devices. We have other tools called the ONNX runtime. It's the Open Neural Network Exchange runtime. It's open source project that defines a format for the machine learning models that we generated between different machine learning frameworks. This means model trained in one framework, like if we get a model trained in PyTorch or TensorFlow, etc., can be converted into the ONNX library and used across various other frameworks. This runtime provides support for optimized inferencing of ONNX model on different hardware platforms, potentially including microcontroller. The latest one we mentioned is the Embedded Learning Library, which is for short is ELL. It's a Microsoft project that allows you to build and deploy machine learning models on embedded platforms like MCUs and single board computers. ELL is designed to run on devices with resource constraints and provide support for optimizing model for target hardware platform. As an example, what we can do for the TinyML. There are many numerous and varied implementation. Particularly, we can see it with the rise of IoT devices. These applications range from predictive maintenance in industrial automation. Like one of startup company, I saw it that they use the sensor to predict whether the engine of the machine, if it generates like specific noise, we can predict how long it will last or it will start to fail over. So they can decide which date it will be essentially necessary to change it or do the maintenance to not affect the production line. Also, like smart home appliances like can adopt the habits, like when we have a smart watch that can monitor the blood pressure, the heartbeat, and over some pattern we can see like if, when the person is sleeping, if there is a short of breath or some pattern of the heartbeat that it's reduced at some point, it can trigger that there is some issue. This implementation already implemented like in many famous smart watches, which can, let's say, call the emergency in case something happen. But what will happen like if there is no network, like internets have some issue in communication. So when we implement it on this machine learning algorithm on the device offline, this will improve the efficiency and the response of the device. Other examples include like agriculture IoT devices, which monitor the weather condition and soil health for optimized crop production. So about the development process, like the developer, how as an embedded developer who want to go to the machine learning world, how usually this will happen. The development process for TinyML involves several key steps. First, model training. This involves using a large system with more computational power to train the machine learning model on the desired task. Let's say like we feed, if we have a vision system that we need to feed it with a large data set of picture to can make decision to see that, to predict what is the shape of the image, inside the image, like this is a cat, this is a car. After that, we do optimization once the model is trained. It needs to be optimized to reduce its size and computational demands to fit the constrained resources of the target device. Then, after we get it, we need to integrate it with the RT thread. So this integration, usually we will write code that allows the RT thread to use the model for the inference. There is already a beta implementation for the RT thread studio. So especially the one is the the TensorFlow Lite for microcontroller. There is already implementation if we check the library. But I haven't had time to try it out. For now, it's support Raspberry Pi and other two SoC. I hope later I will try to port it to the IMX-based board. The latest one is the debugging. Finally, when the system is tested and any issue are fixed, this step might involve a mix of software debugging and validating the output of the machine learning model. So in our concluding slide, we will recap the main point of this presentation. TinyML or Tiny Machine Learning refers to the deployment of machine learning models on resource-constrained devices like microcontrollers. The significant benefit of TinyML include its ability to function offline, provide real-time response, ensure user data privacy, and operate with low energy consumption, as we don't need to use the high-end computer size like the cloud servers all the time. So we can reduce the data exchange between any embedded system or sensors with the server. Also, we talk about the RT thread, a real-time operating system, play a pivotal role in managing the complexities of these constrained devices, providing benefits like improved task scheduling, enhanced resources management, increased modularity, better power management, and improved determinism. We also explored various open source tools that enable the development and deployment of TinyML model, including TensorFlow Lite for microcontrollers, CMSIS neural network, and ONNX runtime, and the embedded learning library. We discussed several real-world applications of TinyML and RT thread, demonstrating the practical impact this technology can have in diverse sectors, such as IoT, wearable tech, smart home appliances, and industrial automation. We also detailed the process of developing and deploying TinyML model on an RT thread-based system, including steps like model training, optimization, integration with RT thread, and debugging. As we look toward the future, we anticipate exciting development in both TinyML and RT thread. With ongoing advancement, we can expect these technologies to become even more powerful, sophisticated, and pervasive across various industries and applications. Your continued exploration and application of these technologies will undoubtedly contribute to this exciting progress, especially to RT thread community and world. Thank you, everyone.